Section 4.3, Homogeneous linear equations with constant coefficients. In this section, we will look at the process how to find the solution of the homogeneous linear equations with the constant coefficients using the auxiliary equations, and three different cases of the solution that might occur, which is case 1, distinct real roots, case 2, repeated real roots, and case 3, conjugate complex roots. Also, find the solution of the higher order differential equations. For this special case of the second order differential equation, which is homogeneous second order linear with the constant coefficient A, B, and C. For the solution form, assume the solution in the form of y equals e to the power mx because the exponential function and its derivatives still remain the exponential pattern. As y equals e to the power mx, y prime is m e to the mx, y double prime equals m squared times e to the power mx. Substituting y prime, and y double prime into the second order differential equation. As we see, there is a common factor e to the power mx multiplied by am squared plus bm plus c, where a is the coefficient of the second order, b is the coefficient of the first order, and c is the coefficient of the y. M squared from finding the second derivative, m from finding the first derivative, or the coefficient from the first derivative. E to the power mx, which is exponential function, is not zero, and it never be zero. Therefore, am squared plus bm plus c must be zero. And this equation is called the auxiliary equation, and sometimes we call the characteristic equation. From this equation, which is a quadratic equation, we can use the quadratic formula to find the solutions to it. The quadratic formula, negative b plus minus square root of b squared minus 4ac, all divided by 2a. The discriminant b squared minus 4ac will be the one that determines whether the solution is in the form of two distinct real roots as case 1, or when the discriminant is greater than 0, or the case that discriminant is 0, that means the two solutions are the same. So this case we call repeated real roots. And the last case where the discriminant is less than 0, we will have the solution in the form of the complex solution. So M1 and M2, it could be in the form of alpha plus minus beta I as a complex number. For the first case, distinct real roots or M1 not equal to M2. For the first solution, using M1, Y1 equals e to the power M1x, and the second solution is e to the M2x. Put together as a fundamental set of solutions or the superposition principle for the homogeneous equation. So y equals C1y1 plus C2 times y2 as the solution in the form of the linear combination of the y1 and y2. To get the solution for this case as C1 times e to the power m1x plus C2 times e to the power m2x. Case 2, repeated real roots. M1 equals M2. For the known solution, Y1, as we did in section 4.2, we used the reduction of order method to obtain the second solution where the Y1 is provided or where Y1 is known. So Y1 is e to the power M1x. With this process, will give us Y2 or the second solution as x multiplied by e to the M1x. If you look at the higher order, for the higher order, so y3 gonna be another x multiplied to it, multiplied by e to the power m1x. For y4 gonna be x to the third, e to the m1x, and so forth. But this case, we look at the second order, we just need two solutions, y1 and y2. With the superposition principle, as y in the form of the linear combination of the two solutions, So we have y1, or we have y as c1 times y1 plus c2 times y2, or y equals c1 e to the m1x plus c2 x times e to the m1x. Here's number 3, the conjugate complex solutions. In this case, the m, or m1 and m2, in the form of alpha plus minus beta I, where alpha and beta are positive real numbers. So we put together in um, the linear combination of the two solutions as c1 times y1 plus c2 times y2. Use the Euler formula, e to the I theta equals cosine theta plus I sine theta, and rearrange the term to obtain another form of the solution for this case as y equals e to the alpha x multiplied by c1 cosine beta x plus c2 sine beta x. So we use the alpha, or the real part, as the exponential term, as a power of the exponential term, and the beta, or the number, or the real number with the imaginary part, as the argument of the sine and cosine. For the higher order equations, we treat it the same way. To form the auxiliary equation, the highest order, or the power n from the nth order of the derivative and the same coefficient. For example, for the n-1 order, the power of the m is n-1. The coefficient is the same as the coefficient of that order, and so forth. Examples. Number 1, find the general solution of the given second order differential equations. As you see, all examples, they are homogeneous, linear, with the constant coefficients. For the second order, we have y equals c1y1 plus c2y2. That's the form that we are going to get as a final answer. For part A, we have 5y second prime plus y prime equals 0. We obtain the auxiliary equation as 5 times m to the second plus 1 times m to the first equals 0. See the second order, power 2, same coefficient. First order, power 1, same coefficient. Now we are going to solve for m. Factor m out, multiply by 5m plus 1 equals 0. We get two solutions as m equals 0 and m equals negative 1 over 5. That means y1 is e to the 0x, y2 is e to the negative 1 over 5x. E to the 0x is just 1. When you write as the general solution, y equals c1y1 plus c2y2, we will get c1 times 1 plus c2 times e to the negative 1 over 5 times x.